Now we know that organic molecules can undergo what we call auto-oxidation with molecular oxygen via free radicals, and this has a very important application in the synthesis of acetone and phenol. So the synthesis of acetone and phenol, which are two very important industrial chemicals. And the way this proceeds is via cumene. As you know that cumene can easily form a benzylic radical, which is exceptionally stable. And because it's exceptionally stable, it can react with molecular oxygen to yield the cumene hydroperoxide, which decomposes to give acetone and phenol, two very important industrial chemicals. Now, it's rare to see an industrial process that gives products that have very, very high value. Okay. Now, how the auto-oxidation mechanism proceeds is as follows. The first thing is an initiation. Okay. So you have an initiation in which the carbon-hydrogen bond is broken by in the presence of an initiator to produce the alkyl radical. Once the alkyl radical is produced, it reacts with molecular oxygen, which can exist as a diradical, to give this product, and then via a coupling, and then that product now reacts with the alkane to yield the hydroperoxide. You see, so basically that's how it happens. That's how it happens. And then you can have a termination step in which two alkyl radicals can find each other, and they are destroyed. See. Now, let's look at the propagation steps, because the propagation steps will help us to see how the net chemical reaction is obtained. As you can see, once the radical is formed, once the alkyl radical is formed, it reacts with molecular oxygen, which can exist as a diradical, to give this intermediate, and that is intermediate now reacts with an alkane, with the alkane, to yield the hydroperoxide and the alkyl radical, the sum of which gives the reaction between the alkane and molecular oxygen to give the hydroperoxide, which we call the auto-oxidation. Now, auto-oxidation is very important because it helps us to understand why food goes rancid. Okay, why is it that food spoils? It has to do with auto-oxidation. Okay, and note here that the steps in the mechanism above are not part of the net equation. The steps in the mechanism that are not part of the net equation must either be initiation or termination. Remember, the net equation is always obtained from the different propagation steps, not the initiation or the termination steps. The net chemical reaction is always obtained from the propagation steps, and that's why you can see here that the net reaction is only obtained from the two propagation steps, which one looks like a coupling and the other one is a hydrogen abstraction. Now, some of the application, some of the ways in which autooxidation occurs are particularly in ethers. Okay, when you have something like a diethyl ether, right, this hydrogen here is susceptible to abstraction. The hydrogen can be easily abstracted, right, because that hydrogen the radical that forms upon abstraction of the hydrogen can actually be stabilized by the effect of the oxygen. Okay, and so these hydrogens are very susceptible to autooxidation, and that's how you can go from a diethyl ether to a hydroperoxides. Now, the bad thing about this is that hydroperoxides can be very explosive, you see, and that's why if ethers are stored for a very long time, they can actually explode because of the formation of hydroperoxides. And that's why ethers need to be dated and used in a timely fashion. Now, light accelerates oxidation, as we can see. Remember, the initiation is promoted by light. And that's why it's always recommended that you use dark containers to store many compounds that can undergo autooxidation, such as vitamins. In the absence of light, the autooxidation is usually a very, very slow process. And please note that compounds that can form a relatively stable carbon radical upon abstraction are especially susceptible to autooxidation, and that's because they can exist long enough. They can exist long enough to couple with the oxygen diradical and then lead to the formation of the hydroperoxide. Good examples of carbon radicals that are very stable include allylic radicals, benzylic radicals. See? Now, let's look at triglycerides, which are a very important part of a healthy diet. You can see that here we have a lot of, we have some allylic hydrogens at this position, and at this position, at this position. Now, these allylic hydrogens are susceptible to autooxidation. See, and that is the reason why triglycerides can actually become rancid and toxic. Okay, and that's how food gets bad. Food gets bad by simple autooxidation. Now, to increase the shelf life of foods like this, you need to use a preservative. And basically what a preservative does is to quench the radical that forms. So the free radical that forms is quenched. And two examples of preservatives include butylated hydroxytoluene, or BHT, or butylated hydroxyanisole. These are free radical scavengers. They will help terminate the free radical because the radical that forms is really very, very stable. And so we can see this example here. The preservatives can undergo a hydrogen abstraction to quench the carbon radicals that form in the first step of autooxidation, right? And basically that leads to the formation of a very, very stable radical. As you can see, the radical that forms in this case, if you look at the resonance form that is obtained, I'm just going to draw that real quick. So you can see here that the radical that forms here is pretty stable. This is not only an allylic radical, but it's also a tertiary radical. And because of this tertiary butyl group, right, it's almost impossible for any radical to try to couple with this radical because of significant steric hindrance. You see, because of significant steric hindrance, and also the fact that this radical is also stabilized by resonance. you see, it will be impossible for this to react further to give anything useful. Other inhibitors other things that inhibit auto-oxidation include vitamin C, which is hydrophilic, and it helps prevent auto-oxidation in blood. In other words, it protects our blood. Vitamin E is also on the other hand, is also hydrophobic, and it also prevents auto-oxidation in cell membranes. Okay, and these hydrogens that have been circled here are the hydrogens that can easily be abstracted and lead to the formation of the oxygen radical, which can be stabilized by resonance. Okay. Now, we learned in chapter 9 and that HX, or a hydrogen halide, will add across the carbon-carbon double bond via the anti-McNichols reaction, especially when peroxides are present. Okay, so in the McNichols reaction, HBr adds to the double bond, and the hydrogen always goes to the less substituted carbon, while the bromine goes to the more substituted carbon. That's what we expect. But in the presence of peroxide, the reverse is the case. The bromine goes to the less substituted carbon, while the hydrogen goes to the more substituted carbon. You see? And the reason is because of the free radical intermediates that are involved. I recall that initiators have very, very weak oxygen-oxygen bonds, and so the resulting radical can be stabilized by resonance. It can be stabilized by resonance, right? Now, once the radical is formed, then what happens is that it can abstract a hydrogen from the HBr. There can be a hydrogen abstraction, and which will lead to the formation of the bromine radical. Now, once the bromine radical forms, the bromine radical now undergoes an addition to a pi bond, as you can see here, an addition to a pi bond, and with the subsequent formation of a tertiary alkyl radical, which is significantly stable. And you can see here that the reaction is exothermic. This step is exothermic. And then what happens is that the tertiary radical can again react with another unit of HBr to yield your anti-McNichols addition product, and the formation of a bromine radical, which is significantly stable, really very stable. And you can see that this is more exothermic, because of course the product that is being formed is more stable than the reactants that we began with. See, now the tertiary radical forms, we already learned with bromination, goes through a lower transition state than the secondary radical, and there's a huge energy difference between the two of them. Okay, and so we remember that most of the radicals in solution at the moment will give bromine radicals, and that's because of the hydrogen abstraction by the initiator. Okay, most of them will give bromine radicals, and once the bromine radicals form, then the reaction continues. Okay, all right. Now, the anti-McNichols addition of HBr is generally spontaneous or product favored. Okay, we already learned that. Yet, the radical addition of HCl and HI are generally non-spontaneous. And the answer to this is to look at the enthalpy change for the propagation steps of these reactions. Okay, so if you explain the sign for the entropy term in each process, so you have HCl, you have HBr, and you have HI. You can see that in the case of HCl and HBr, the first step, propagation steps, has a negative enthalpy change.